Hello everyone, we start chapter 6, set theory, and section 6.1, which focuses on definitions of set theory. Um, we start with the definition of subset and proper subset and set equality. As you remember in chapter 1, we defined uh, subset, but here we are going to define it in a more symbolic way using uh, you know what we learned in the chapters 2, 3, and 4 using predicates. So here is the definition of subset. We say A is a subset of B if and only if for every x. If x belongs to A, then x belongs to B. And in order to define uh, A not being a subset of B, we need to negate this universal conditional statement, which will become an existential statement like this. We say A is not a subset of B if and only if there exists some x such that x belongs to A and x does not belong to B. Please note that in the definition of subset, we had a universal conditional statement, so its negation becomes an existential statement with the negation of this conditional statement. You know that the negation of a conditional statement is the premise and the negation of the conclusion. That's why the negation of that looks like this. And this is a definition of A not being a subset of B. The next thing is a definition of proper subset. A is a proper subset of B if and only if two conditions are true. First, A should be a subset of B, and second, B should not be a subset of A. And if you remember from chapter 1, we said we can replace the second condition with A is not equal to B. Later on, when we define set equality, you will notice why we can replace the second condition with A is not equal to B. Okay, so the next thing is the definition of set equality. Given two sets A and B, we say A equals B, and we show it with this symbol if and only if every element of A is in B and every element of B is in A, correct? So based on the definition of subset, we can symbolically show the definition of set equality in this way. We can say A is equal to B if and only if A is a subset of B and B is a subset of A. Why? Because every element of A is in B, so A is a subset of B, and every element of B is in A. So B is also a subset of A. Next, we are going to see an example from the book regarding set equality. Example 6.1.3. In this example, let's define set A and B as follows. Set A is set of all integers like m such that m is equal to 2a for some integer a, and B is the set of all integers like n such that n is equal to 2b minus 2 for some integer like b. And the question here is A equal to B or not? To answer this question, we say yes, and to prove it, we need to prove two different things. First, we need to prove that A is a subset of B, and second, we need to prove that B is a subset of A. In the first part, I'm going to prove that A is a subset of B. So to do this, I suppose that X is a particular but arbitrarily chosen element of A, correct? So X is an element in A, which is particular but arbitrarily chosen. And then I use a definition of A and say there is an integer like A such that x is equal to 2A. That's based on the definition that we had here. Then I say let B becomes A plus 1, so B is an integer because it's the summation of two other integers, right? And also 2B minus 2 is equal to, by substitution, we can replace B with 2A minus 2A, I mean, we can replace B with A plus 1, so we'll get 2 times A plus 1 minus 2. So 2B minus 2 becomes 2 times A plus 1 minus 2. If we further simplify it, we'll get 2A plus 2 minus 2, which is equal to 2A. And since x was 2A, so we reach to x. So we conclude that x is equal to 2B minus 2, right? So based on the definition of set B, since any element in the form of 2B minus 2 is a member of B, we can conclude that x is also a member of B. X is an element of B. So we started with the supposition that x belongs to A and x is arbitrarily chosen, and we conclude that x belongs to B. So based on the definition of subset, we can conclude that A is a subset of B. The second part also can be proved in a very similar way. We need to prove that B is a subset of B in the second part. To do this, we suppose that X is a particular but arbitrarily chosen element of B, and then you use the definition of B to say that there is an integer like B such that X is equal to B, 2B minus 2, and then we define A equal to B minus 1, so 2A is equal to 2 times B minus 1. By further simplifying it, we'll get 2B minus 2, which is X. So we prove that X can be written as 2 times A, where A is an integer. And then as a result, we can say by the definition of A, we have proved that X also is an element in A. So with from the assumption of X belongs to B, we reach to the conclusion of X belongs to A. So the second part is also proved. So B is a subset of A, and then we have proved before that A is also a subset of B. From these two proofs, we will conclude that A is equal to B based on the definition of set equality. Alright, so the next definition is the definition of four operators amongst sets. So the first operator is union of A and B. Okay, we say the union of A and B, which is denoted by this symbol, is a set of all elements that are in at least one of A or B. And you know, for this definition, I'm going to show you this equation. This equation is the symbolic definition of union of A and B, which basically says union of A and B is a set of elements X belongs to U such that X belongs to A or X belongs to B, because we said it belongs to at least one of the sets A or B, correct? That's why we need to put an or, a disjunction between X belongs to A and X belongs to B. Now, what is U? U is called the universal set, which contains sets A and B. So A and B are two sets that are subsets of the universal set U. Okay, so in order to illustrate this definition, uh, we usually show it in a Venn diagram, which basically gives us schematic and symbolic um, form of the definition of union. Um, Here is the Venn diagram of the union operation. This is the first diagram, the leftmost diagram. Okay, so I'm going to explain to you what this Venn diagram represent. Basically, we have a rectangle which we call it U, the universal set. So the rectangle represents the universal set, and there's two circles inside that rectangle represent sets A and B. In this case, the left hand side circle is A and the right hand side circle is B, and basically A and B can be two arbitrarily chosen sets and two arbitrarily chosen subsets of U. That's why we don't rule out the possibility of intersection between A and B. That's why some part of A is in B and some part of B is in A. This part I'm talking about. A and B have some intersection because we are going to consider the most general case, correct? And so the Venn diagram of union of A and B basically shades the region that represent A union B. So if we assume that the left circle represent A and the right circle represent B, so the union of A and B should cover both circles A and B. That's why we shade both circles like this. As you see, there's a shaded region with light blue that represents a union of A and B. In the similar way, we define intersection of A and B. So the intersection of A and B, denoted by this symbol, is the set of all elements that are common to both A and B, and this is the definition of the intersection of A and B in a more symbolic way. We say it is equal to the set of all elements X belongs to the universal set U, such that X belongs to both A and B. And here is the Venn diagram for intersection. Again, we have U as a rectangle, A and B as two circles, and the area shared between A and B here is shaded with blue. That's why it represents the intersection of A and B. The next definition then is the definition of difference of B minus A, or relative complement of A in B. We denote this set by this symbol. Basically, we write B minus A, and this represents the set of all elements that are in B and not A, correct? So the set of all elements in B that are not in A. So in a symbolic way, we can write it in the form of this equation, where B minus A is a set of all elements X belongs to U, such that X belongs to B and X does not belong to A. And the last definition is a definition of complement of A. This is the last operator that we have. And basically it says complement of A denoted by A superscript C, which is the set of all elements in U that are not in A. Symbolically, we show this, definition using this equation right here. We say A superscript C is equal to the set of all elements X belongs to U such that X does not belong to A. Now let's look at the Venn diagram of the difference of B and A and the complement of A. So the third Venn diagram right here shows B minus A. Basically, the shaded area covers all the area inside the circle B minus the area that is shared with A, correct? So it shades B, but not all, not the whole circle of B. It it doesn't shade the shared region between A and B, because B minus A means the set of all elements in B that are not in A. So we should keep the circle A white. We should not shade any part of the circle A in this diagram. And the Venn diagram of AC, which is the complement of A, looks like this, the last diagram. Basically, since A complement of A means all the elements that are not in A, we need to shade the whole region inside the rectangular area that represents U, and keep the area, the circular area of A unshaded, because we are going to include everything that are outside of A. Alright, so here we prove two different theorems. First, we prove the uniqueness of empty set, and then we prove a set with no elements is a subset of every set. So this is a theorem which basically says the empty set is a subset of every other set. And it's even the subset of itself. So we can say the empty set is a subset of every set without any exception. So let's first prove the theorem 6.2.4 using contradiction. Basically, the theorem 6.2.4 says if empty set, which I'll show you later why we give it a symbol. This is the symbol for empty set. We say if empty set is a set with no elements and A is any set, so A is an arbitrarily chosen set, an empty set is represented by this symbol. Then we are going to prove that empty set is a subset of A. To prove it by contradiction, we suppose not. We suppose that empty set is not a subset of A, and as a result, there would be an element in the set empty set that is not an element of A. Why? Because of the definition of subset and not being a subset. And here we reach a contradiction. Why? Because we said there is an element in the empty set that is not an element of A, but there can be no such element since empty set has no element whatsoever. So this is a contradiction. So we have proved theorem 6.2.4. Now let's prove the uniqueness of empty set. The uniqueness of empty set basically says there is only one set with no elements. And this unique set is called the empty set and is represented by this symbol. That's why we give it the specific symbol, because it's unique. To prove the uniqueness of empty set, let's suppose that E1 and E2 are both sets with no elements, okay? And then based on the theorem 6.2.4 that I just proved right here, we say E1 is a subset of E2. Why? Because E1 is an empty set, so it's a subset of any set, so E1 is a subset of E2. And also we can have the same argument for E2. We can say since E2 is an empty set, it is also a subset of E1. Since E1 is a subset of E2 and E2 is a subset of E1, based on the definition of equality of sets, we can conclude that E1 is equal to E2. So basically E1 and E2 represent the same set. So we conclude that even if we have two sets with no elements, those two sets should be equal. So we have a unique empty set, which will be represented by this symbol right here. Okay, so it's time to introduce a few symbols and a few notations regarding the unions and intersections of a collection of sets. Let's assume that we have a collection of index set like this, A0, A1, A2, and so on and so forth, that are subsets of a universal set U. And let's assume that we have a non-negative integer like n. Then we say the union from for I from 0 to n of A sub I, or union of A sub I for I from 0 to n, is equal to the set of all elements like x belongs to the universal set U, such that for at least one I from 0 to n inclusive, x belongs to AI. So x should belong to one of the AIs, to at least one of the AIs, where I is a number from 0 to n. I is an integer from 0 to n. And the second notation is this one. We say the union of AI for I from 0 to infinity. This is the symbol that we use for infinity. This is equal to the set of all the x's belong to U, to the universal set, such that x belongs to AI for at least one non-negative integer I. So this I is a non-negative integer, and we have to have at least one non-negative integer like I, such that x belongs to AI. So the first two symbols were about unions of multiple sets. The next two are about the intersection of multiple sets. So the third notation is this: intersection of AI, I from 0 to n, is equal to the set of elements x belongs to A, such that x belongs to AI or A sub I for every I from 0 to n inclusive. And also we have the intersection of um, AI for I from 0 to infinity, which is a set of all elements in U such that element x belongs to AI for all non-negative integer I, correct? So it should be so x should belong to every I from 0 to infinity. Okay, now let's see a few definitions regarding sets. Uh, if we have two sets like A and B, these two sets are called disjoint if and only if they have no elements in common, or symbolically we say A and B are disjoint if the intersection of A and B is equal to empty set, correct? And also we have another definition. We say let's assume we have sets A1, A2, A3, so on and so forth, and these sets are called mutually disjoint, or they are called pairwise disjoint or non-overlapping if and only if no two sets AI and AJ with distinct subscripts have any elements in common. More precisely, or in a symbolic way, we can say for every I and J from 1, 2, 3, so on and so forth, A sub I intersection with A sub j is equal to empty set whenever I is not equal to j, because if I is equal to j, then intersection of any set with itself is equal to the set itself. But here in the definition of mutually disjoint sets, we say a intersection of ai and aj is empty set when I is not equal to j. Okay, so now we have defined mutually disjoint sets. We are ready to define the partition of a set. Here is a very important definition. We say a finite or infinite collection of non-empty sets A1, A2, A3, so on and so forth is a partition of a set A if and only if two different conditions are true. The first condition is A is the union of all AIs. What do we mean by the union of all AIs? We mean the union, the big cup right here, union of AI for all the I's that are available. The union of all the AIs should be equal to A, okay, where A is the set that we are going to get the partition. We are going to partition it. And the second condition for partition of a set A is that the members of that partitions, meaning A1, A2, A3, so on and so forth, these sets which are members of the partition are mutually disjoint. Okay, so they should be mutually disjoint and their union should be equal to A itself. A is the set that we are going to partition. And if you look more closely to into this definition, you see that there is another condition that is sort of hidden inside the definition. You have to take a closer look to find it out. As you look at here, we say a finite or infinite collection of non-empty sets. So basically, none of the sets A1, A2, A3, so on and so forth, none of them should be equal to the empty set, correct? So that's sort of the third condition that you don't see it explicitly in the definition, but it is mentioned at the beginning of the definition. Okay, so in order to see, in order to get a better understanding of this definition, we are going to solve an example of the book, example 6.1.11, which is about the partitions of sets. Let A be a set including the first uh, six positive integers, the integers 1, 2, 3, 4, 5, and 6. And we define three more sets. We say A sub 1 is a set including 1 and 2, A sub 2 is a set including 3 and 4, and A3 is a set including 5 and 6. Now the question is the set including A1, A2, and A3 is this set a partition of A or not? And the answer is yes, because it satisfies all the conditions that a partition needs to satisfy. First of all, not A1, nor A2, nor A3 are equal to empty sets, right? So none of these three sets are empty sets. That's the beginning condition. Then the condition number 1 here says A should be the union of all the AIs. Basically, A should be constructed using A1, A2, and A3. So if you look at the sets A1, A2, and A3, you see that by getting a union of these three sets, we'll get the set A itself, which has 6 different elements. And finally, we need to check the second condition, which says the sets A1, A2, and A3 are mutually disjoint. So as you see, the sets A1 and A2 and A3 are mutually disjoint. Why? Because A1 and A2 has no common members or has no common elements. A2 and A3 has no common elements. But this is not enough. We have to check A1 and A3. A1, intersection of A1 and A3 also becomes the empty set because A1 and A3 has no common elements. So finally we conclude that A1, A2, and A3 are mutually disjoint, and based on the definition of partition, we conclude that this set right here, the set containing A1, A2, and A3 is a partition for A, where A is this set. Okay, so the last definition that we are going to give in the sixth chapter is the definition of a power set of A. So let's assume that we have a set like A. Okay, so the set A is given. The power set of A is denoted by this symbol P of A, and is the set of all subsets of A. So power set is a set of all subsets of A. What does it mean? Let's look at an example to clarify what this definition actually means. We see example 6.1.12, which basically asks us to find the power set of a set including two elements. The elements are letter X and letter Y. So we are going to find the P of X and Y, the P of a set including X and Y. P of X and Y means the power set of set X and Y. So based on the definition, the power set is the set of all subsets of X and Y. Now let's think about all subsets of set X and Y. Based on the theorem that we proved before, we know that empty set is a subset of any set. So based on this theorem, we can conclude that empty set is a member of the power set of any set, right? So x and y is also a set, so empty set belongs to P of x and y. What else? We know that every set is a subset of itself. So the set x and y is also a member of the power set of x and y. What else? We know that the set including only x and the set only including y are also subsets of the original set x and y. So both of them are two members of the power set of x and y. So the power set of x and y has a total of 4 elements. The first was the empty set. The second and third was the set including only x and only y. And the last one is the set itself, the set of elements x and y itself. Okay, so the power set of an element with two members has 4 different elements. In general, if we have n elements in A, then the power set would have 2 to power n elements. And this can be proved. We are going to prove it later in this course. So keep in mind that, for example, in this case, where n is 2, we have 2 to power 2, which is 4 different members for the power set of set including x and y. Now let's look at a few more notations and close this chapter with these notations. Let's assume that x and y, a and b are two real numbers such that a is less than or equal to b. We define 4 different notations. The first one is an open interval a and b, which is an open interval. Why? Because this interval does not include its endpoints, which are a and b. So this is a set of all real numbers like x, such that x is between a and b exclusively. X is greater than a and x is less than b. Then we define another interval, which is this closed interval of a and b, which includes their endpoints, which includes its endpoints a and b. That's why we call that the closed interval. And it's set of all integer, the set of all real numbers x, such that x is greater than or equal to a and less than or equal to b. And the next one is a combination of an open and a closed interval. These are semi-open intervals. The right hand side is closed, the left hand side is open. We represent the open end with a parenthesis like here, right here, and we show the closed end, which is the right end, using a bracket, right, like this. So this interval is a set of all elements in R such that x is greater than a and x is less than or equal to b. So b is included in the interval, but a is not. And similarly, we define a semi-open interval like a and b, which includes a but does not include b, and is defined as a set of all real numbers such that x is greater than or equal to a, but x is less than b. Okay, so using the symbols infinity and negative infinity, we can define four more intervals. The first interval is this one, the interval of a and infinity, open interval of a and infinity, which is equal to the set including the set of all real numbers such that x is greater than a. And then we have a semi-open interval like this from a to infinity. Obviously the endpoint that is not infinity is closed, so the a endpoint is closed, so it includes a, so it's the set of all real numbers such that x is greater than or equal to a. And then similarly we have an open interval like negative infinity and b, and it's defined like this, the set of all real numbers such that x is less than b. And also we have another interval which is negative infinity and b. So here is a problem in this notation. Please note that we have a bracket here after b, and we have a parenthesis before negative infinity. There should be a problem in the textbook. So the part that we have, the endpoint that is negative infinity should always be open, should always be represented by a parenthesis, while the closed part, which is the closed endpoint, which is b, should be represented by a bracket, correct? So if we have a bracket in the closed end, and we have a parenthesis in the open end, in the left end, and it's defined as all the real numbers such that x is less than or equal to b. So by introducing these notations, we close chapter 6.